My name is Travis Collins, and I'm an engineer with Analog Devices. In this presentation, I'll be discussing some new open source tooling we have developed for JESD-based devices, like SDRs or high-speed data converters, to make them easier to use and to optimize their configuration. This will include a basic background on JESD204, what it is, how it works, how you do configuration of devices that utilize JESD. The new tool, we'll introduce a new tool, Pyadi-jif, and we'll go into a real-world example using some real hardware and unit radio. So the JESD204 specification is a JEDEC specification, similar to something like PCIe that's designed to work with high-speed data converters or high-speed links between FPGA data converters or even ASICs, things like that. This is a departure from the original, or I would say LVDS CMOS dual data rate style links between the older generation of devices like, say, like the 9361 transceiver that's in a device like Pluto, which use that style of interface. So this is really a shift when we're going up in higher bandwidths, where we need to share a lot more data between the data converters and, say, an FPGA or an ASIC. And you need something like JESD on transceivers like 9371 or any high-speed data converter. So this is really where the industry has been pushing for the last, I would say, decade. And you'll be, if you're using a device like the similar on the right, or something like the EDIS N310, or a high-speed instrument or something like that, you'll be using JESD. Now, why should you really care about this, or why would you want to know at all about JESD? So if you're doing something like changing the sample rate, if you need to reduce the power of your current device, if you're using a high-speed converter or transceiver, if you want to move between FPGAs, so if you're not using, or if you're using like a Xilinx kit and you want to move to an Intel, or if you want to move to a different grade of FPGA, you really need to understand how JESD works and the different elements that are involved when kind of manipulating the clocks when we're talking about JESD-based devices. So just to kind of give a brief introduction or to kind of focus things a bit here, this is a picture of a standard FMC card that you might get from ADI or Maxim or TI. This one specifically here is the 809081 FMC card, and this will contain a high-speed DAC, high-speed ADC, and then this screen board on the left is a standard Xilinx kit, a ZCU102 that you would plug up to this board. And then for reference, we have just Pluto for size. So this would be a common place where you would start developing a system before you might have a custom solution that you would have for an end product. Now, if we zoom in, these data converters, or this link between the FPGA and the data converters, will be using JESD204. And the links that are between the two devices will be in the tens of gigasamples a second, or gigabits per second. So very, very high throughput between these two devices. And JESD is really designed for this, where we have where data can range from, say, like 325 megabit per second all the way up to 32 gigabit per second. So very, very fast links, similar to something like PCI Express. Now, conceptually, looking at this in a bit more detail, JESD will have what we call links, which will be the connections between the data converter and the FPGA. A link will have a number of lanes. So these are like the physical connections that go between the converter and the ASIC. And then if you have multiple converters, each one will have their own independent link. Technically, you can have multiple links on a converter, but that is kind of an uncommon use case. And then the secondary aspect here is that each link will have some system reference or some reference clock, or sysref as we call it, that's providing synchronization between those two devices. And this is usually provided by a parent clock device. Now, architecturally, this can be really useful because we can separate out the converter itself from the FPGA or ASIC. We don't have to have them tightly coupled together or tightly placed on a PCB. You could have something like the ADCs and DACs located up in your tower, and then run, say, like fiber down directly from the converter to a processing closet or something similar, where you would have banks of FPGAs or banks of GPUs. So you don't necessarily need a big, power-hungry FPGA mounted next to your antenna elements. You can kind of separate them to the two if you really want to do that. Now, the big paradigm shift here is that we're switching the connection between the FPGA and the converters from a lot of slower speed data links to these really high speed links where we have a lot fewer of them. So you can think about this at the board level, where we have just an example of, I would say, more traditional LVDS style interface, where on the left here, where you have a lot of differential pairs that need to be connected from the data converter to your processing component like an FPGA. And here you can see that we have roughly like 15 pairs. That's a lot of things that need to be laid out. They need to be matched in length, which is why you see this like tromboning effect or layout being done on the board. And that's to make sure that the lengths between all of the connections between the converter and the ASIC or FPGA, what's on the other side, are the same. Now with JESD on the right, we have a lot less pairs because we can run them at higher speeds, and they don't necessarily have to be matched in length. This is because we can do things in the digital domain that allows us to compensate for that, and we can deterministically know what the latencies are between the converter and our FPGA or processing unit. However, this complexity of running the links at tens of gigabits per second shifts really the paradigm or the complexity from the layout into the FPGA or into the protocol that we're using. So this is really where the JESD protocol comes into play and the standard comes into play, similar to PCIe. Similar to like any comm standard, you would have a number of layers that are associated with it that would take care of things like scrambling or error correction or link management to make sure that things are coming up in a certain order, we're having like metadata inserted in the correct way, you're correctly recovering clocks, and you're managing all those things. So you have these different layers that kind of handle those different aspects of a protocol, of a frame or a header or metadata, and manage that system. So we're shifting that complexity from the layout all the way into the FPGA, into the ASICs themselves. So fortunately, if you're using a ADI device, like an ADI converter or ADI clock chip, we have a number of resources that really help you here. So we offer what we call the JESD interface framework. That includes full reference designs with different converters, clock chips, and FPGA families. So we have them for Intel and Xilinx FPGAs, depending on what you're using. These include drivers, HDL, tools that help you debug and kind of do manipulation or changes of the JESD links, really to help you, make sure out of the box things are functioning for you and you have a complete system to start from. And then you can kind of transition over or customize it as you wish. So switching gears a bit, let's actually talk about how you do configuration with JESD. This is really the heart of what we want to talk about with the tooling around Pyadi-jif. Before we kind of dig down deep, I just want to talk a little bit about what clock chips are and how fundamentally PLLs work, because that's really what clock chips are. I would say they're fancy PLLs. And this will make the discussion make a lot more sense when we kind of dig into JIF and what it's really doing. So this diagram here is of a clock chip, the 9528 that we make, but similar across the industry, they'll have a similar structure. There are 5 main components in this clock chip. On the left is PLL1. In the green here is the sysref generation. We're just going to ignore these for just the discussion. They're really not that important for this context. But in red are the pieces that we really care about. So how this clock chip works is that we have some reference, which is in this case a VCXO, just a crystal that's hooked up to the clock chip, and that will be at some reference frequency that we pick based on the device. And that frequency will go through a PLL2 here, be divided down and then fed back and divided up. And we can generate a number of different frequencies based off of this equation that we have here. And then we take that frequency, which we call VCO, the VCO frequency, and then we divide it down based on some divider selection that we choose. So we can get essentially multiples of this VCO out, and these would feed a ADC and FPGA. And you would use this to define things like the sample rate that you want to run at, or the reference that you want to use to the device, and that would reflect the eventual configuration of your system. So when you're configuring this device, which is feeding out to the converters, to the FPGAs, you need to be careful on how you pick these values or these dividers inside. So this N2 or R2, or it would be kind of unique to every clock chip. And then the output dividers, this D sub X here, that would feed either like a sysref or directly clocking a converter, or feeding into like the SerDes lanes. So this allows you to get a different range of frequencies based on what your VCXO input reference is and how you pick the dividers, but it's not endless. So you need to be careful on how you pick these different components and their interrelationship between another. So now if we switch to kind of a high level view of what these JESD, or these kind of, I would say, disjoint clock devices function or are laid out, we have this outline where we have a clock chip, which is feeding our FPGA and is feeding our converter, and are responsible for providing these device clocks and references that allow us to maintain this link that is between them. And the thing that you have to know is that when we're feeding these references, they're feeding actually usually into PLLs that exist within these parts. So we need to make sure that those references and the PLLs inside these different components are configured correctly. So these are typically for SerDes, which are this PLL on the FPGA is for the SerDes. We'll have one on the converter, and we might even have an additional PLL that is for the data converter itself, or an external PLL that we need to interface with again. So there's a lot more complexity, and that equation that we kind of showed for the clock chip kind of gets bigger and bigger and bigger, and you have these interrelationships between it. And this is really where the complexity of the system comes in, and being able to figure out how you need to program these different components, you need to make sure that they're all matching one another. And then if you want to change, say, sample rates, what impact does that now have? So when you have all those quantities, you need to feed them into tools like the device tree on the Linux side, and they need to drive the synthesis process on the on the HDL side. So if you're not familiar with device tree, it's kind of like the BIOS on an x86 machine, where you have configuration that's specific to drivers or some interrelationship between drivers. And in the case of JESD and clock chips, we're defining things like the JESD parameters, or the rates, or the dividers that we're using. And then on the HDL side, we're configuring things like the transceivers that are inside the FPGA. We're configuring the number of links that are inside, that are the cores will kind of create during synthesis time. And this all needs to be done by the user, and these components need to be able to match one another. So there's a lot of complexity that's involved when doing this. Now, the drivers do a lot of the math for you to make this function, but you need your hardware, and this is kind of where we're trying to fill the gap and to handle a lot of the complexity that's involved at the system level with some of the new tooling that we've been working on. This is really where JIF comes into play. So JIF is a configuration library and interface layer. So it has like a web API, it has a desktop app, it has a CLI interface, and obviously it's a Python module or a library that we can directly interface with. And then JIF feeds or sits on top of these other tools like the Linux drivers or the NoOS components, or the data structures there, as well as the IP cores or their synthesis tools or their constraints, and eventually the hardware itself. And so at a very, very high level, JIF, or Pyadi-jif, JIF for short as we call it, is really the glue between the logic and the rules that you might see in a data sheet or the understanding in a data sheet and the actual tools or the software interfaces that drive the different hardware components. So it's going to allow you to interface with kernel drivers, the FPGA constraints, like bare metal structures that you might use with our bare metal drivers, and allow you to map a configuration or an idea of a configuration like a sample rate into what really that means when you're actually talking and configuring hardware. So internally, JIF will model constraints, dividers, features of different components in a class structure. So we have models for every different component, or I want to say every different component, but components we support, we have models for like ADCs, DACs, mixed signal front ends, different clock chips, different FPGA families, and we can combine their constraints together in a common problem where we figure out what common configuration you would need based on some input requirements that you have. So at a very, very high level, when you really start with JIF, you provide some input that would be sample rate or JESD mode, or some VCXO that you want to use, or even if you don't know that, maybe a range of VCXOs. And then JIF would internally calculate what the clock chip PLL settings are, what the FPGA settings are, what the converter settings are, and then generate artifacts for you to use inside the drivers, inside NoOS, or inside your HDL generation process. And then really kind of collect things together and manage all of those constraints in a consistent way for you. So internally, mathematically, JIF models the different components and converts them to like equations. So we just have an example of a clock chip here where we're taking those PLLs and we're converting them to linear and nonlinear equations. And then we use different solvers to determine what are the optimal values of certain dividers or certain PLLs inside the parts based on some input that you have. And this is kind of a pretty challenging problem because the equations that you get are nonlinear, they're mixed integer. We call them min LP problems, but we can use off-the-shelf solvers to solve these. The two that we're primarily using now are called Cplex and Gecko, and they can be directly installed through pip today. Now, when you're actually using the library, there are two main approaches that you can use. One is at the component level, and then the other is at the system level. They're both documented, but I'll just kind of go through them one by one. So we just have a little bit of code here on the left where we're just taking a clock chip, this case the 9523. We're setting some constraint. You don't have to define this at all. We're setting a VCXO. This could be a single value or range, depending on how you want to set up your system. And then we're requesting some output clocks. And then when we ask the solver to determine what they are, we get this structure on the output, which will give us the input dividers that we want to use, the output dividers, the VCXO, and all the rates. And it will tell us even if something is not feasible to do. Then the second perspective is from the system level, where on the left here, we use this system class, and we're providing it the converter name, which in this case is the 9680. We're providing the clock chip name, same as before, the 9523, and then some FPGA family. And then we can further kind of expand upon the specification where we're inputting all these like letters M, LM, N prime, K, F are all related to the JESD parameters. And then we're adding an FPGA kit. We have, there are a number that we can just directly support, and it will provide the FPGA constraints there. And then we're outputting the configuration once we solve for that kind of sample rate that we want to run at. And you can see here, it's similar to what we saw in the last piece where we're getting all the dividers that are associated with that clock and the FPGA. And we're seeing this is the system reference. This is the FPGA reference. This is the ADC clock reference that we want to use. The converter is directly clocked, so that's why there's really no configuration here. And then we get the different components related to the FPGA. So for example, in this case, we're using the QPLL. And if you're familiar with Xilinx FPGAs, you'll have like QPLL, the CPLL, and internally you can actually force it to do either one. So I know that was quick, But just a kind of a recap at a high level, what JIF really does is it takes in the definition of the hardware that you have, the converter name, some constraints that you might want to apply, some rate that you want to run at, certain optimizations you can provide as well. And then it internally determines how to generate configurations for all the components from the converter to the clock chip and to the FPGA. Okay. So in the final section, we'll just talk about actually translating the JIF configuration over to real hardware and then visualizing using GNU Radio. So to do this, we're actually going to rely on another Python module that we maintain called Pyadi-jif, which allows you to do device tree manipulation. So I don't want to dig deep into this right now, but if you want to learn more about this, it's on our GitHub page. It's part of the Analog Devices organization, and it provides kind of an easy interface to remotely manipulate and control the device tree. And we'll be using this to translate that configuration to a device tree update that we'll use. Now in this case, or in this example, we'll be using this FMC card called the FMC DAC2. This is kind of the simplest example that I could find where we have a gigasample ADC, the 9680, a gigasample DAC, the 9144, and then a clock chip on board, which is the device in blue on the right, kind of on the underside of the FMC card, which is responsible for providing clocks to both the DAC and ADC. So just to give you an idea on the clocking diagram here, on the diagram on the left, we have the clock chip, which is feeding both the DAC and ADC, and then the FPGA, which be kind of connected to that FMC connector. Now, what we need to do is take the VCXO, which is at 125 megahertz, feed that into PLL2, determine the PLL2 configuration, then feed that to the output dividers, and then that gets fed as the ADC clock, as the ADC reference, as the FPGA clock, and the FPGA sysref as well. And we need to make sure that these, since we're primarily looking at the RX side here, are reflective of the sample rate that we want to run at. Okay, so to actually do this, what you need to do is update device tree. And we do this automatically, but I just want to give you an idea of what happens. So here on the right, we actually have a device tree node of the clock chip that we're using, the 9523. And the top half will contain kind of the basic configuration of the device and the VCO frequency that we want to get to. And then the lower half are the nodes that are specific to the different outputs that we want to configure. So this will be the clock to the FPGA called the FMC clock, the sysref for the ADC, the sysref for the FMC card, as well as the ADC clock, which is kind of directly top clocking the converter in this case. Now, from the perspective of JIF, what this looks like is this configuration here on the left, where we're just defining the converter. Technically, you can define both converters, but we're just going to be looking at the RX side. We're setting our FPGA kit, which is an ultra-scale kit, ASIC-102. We're telling it to use the CPLL, which is what the FPGA reference design is doing. We're going to use direct clocking, so feeding the ADC directly. And then we're going to change the standard sample rate from 1 gigahertz to 500 megahertz in this case. And when you run this, JIF will give you this configuration on the right for the clocks and for the FPGA itself. So to load this, we actually have two options. One is that you can use just add a few snippets of code to the bottom of that kind of JIF code where we're just calling ADI-DT directly. Or alternatively on the right, you can actually convert the output to a JSON file, and then we can load that into the command line, which might be a little bit easier to do for some. Okay, now, so moving over to GNU Radio, here we just have a little flow graph set up here with using the GRIO blocks. We can see that we're using just the 9680 driver, the same part. that we showed in JIF, and we're just pulling out one of the channels. So just voltage 0, which is the first channel. And then on the bottom, we're using the attribute source to actually read out the sampling frequency so we can directly determine that we're running at that 1 gigasample a second rate. So we'll hit run here. And I'll auto scale. We just see some data coming in. And we can see that we're running at that 1 gigasample a second rate. And since there's actually a DAC on this board that's being looped back, we see that at roughly 40 megahertz here. And we can use this as a reference when we update the frequency. So we'll stop this. And then we'll go over to our VS Code instance here. And we see just the same configuration as we had before. So we're creating that system object. We're defining our development kit using CPLL. And then we're just going to change the sample rate to 500 megahertz in this case. And I'll just print out the lane rate and what the lane rate over 40, which is typically referred to as the device clock. And then the bottom half, we're just taking that new configuration, we're feeding it to ADI-DT, which is going to talk to the board and update the configuration for the clock chip. Bring up that terminal, just run this script. See that configuration is printed out. And we have a lane rate of 5 gigabit per second and a core clock of 125 megahertz. Just waiting for the board to reset here. You can swap over to just the other terminal. Just make sure we're up. And then we can just check to see if our JESD lanes are up by using this JESD status tool. And we can see now that the lane rate is at 5 gigabit per second, and our core clock here is at 125 megahertz. All right, now swapping back into GNU Radio. So we're just going to update this bandwidth because the sample rate is not 1 gig anymore, or 500 meg, just to reflect that correct position of the plot. And we see that the attribute read out is 500 megasample per second, and then our new position is at 40 megahertz here. So the frequency matches what we expect, because beforehand it was at 40 megahertz, so this directly matches that. So we're not playing any tricks here with kind of changing this just the attribute. We're actually changing the real sample rate of the device, and the tone is still where we expect it to be. Okay, so just to recap what we talked about, so just to add in this extra part when we're actually moving to hardware, we're able to take, as we originally talked about, those hardware definitions, that configuration, things like sample rates, feed that into JIF, which will map that to the actual configurations we need to plug into the devices, and then we're kind of piggybacking off of ADI-DT to manipulate the device tree for that configuration that we're using. If you want to learn a little bit more, there is source available, there's documentation available for both of these projects on GitHub and through GitHub pages today. If you do have questions, please reach out on Engineer Zone for support, or I'm available on GitHub through @TFCollins. But if you have any questions now, over Zoom or over Matrix, I'd be happy to answer them. I'll be available in the ADI channel as well if you have more questions. Thank you.